Okay, this video is your introduction to experiment 18, air column resonance, the speed of sound in air. And I believe back in September, when I did the vector table experiment and the centripetal force experiment with the little spinning bob. I performed this experiment too, so I recorded it. We will be doing. You will be seeing the physical experiment. It's not a simulation. I performed the experiment, and you can get the data off the video. Unfortunately, it's not until the last video where we do. I performed the experiment with I think a 512 hertz tuning fork, a 1000 hertz tuning fork, and then a mystery tuning fork. And it's not until I get to the last tuning fork that you actually get to see the apparatus. I didn't think about it at the time. I was just worried about getting the data, and I didn't actually show an image of the tube. I apologize for that. But in the last video where we look at the mystery tuning fork, you'll see the apparatus. It's just a long 1 meter tube with a plunger on one side. We don't have the kind that we used to have. You used to have a tube with a little canister of water that you would raise and lower, and you would raise and lower the water with the tuning fork over it. And that was a nice device, but a lot of those were made of glass, and if they tipped over, broken glass, big mess. So we stopped using those, and we use the plastic tubes now. Okay, so why is it not showing there? We, of course, with every experiment, you do the advanced study assignment. You read the experiment, and you'll be able to answer these advanced study assignments. It's all there is no TI or CI. It's all the questions are legitimate questions. Okay, so we're going to talk about the air column resonance, the speed of sound in air. And if you've watched the videos on chapter 17, it talks about like the resonance in pipe organ tubes, and that's sort of what we're doing. We're going to select out a particular or the tube when it's at the correct wavelength, or actually multiples of quarter wavelengths, that you'll hear a resonance. I don't know that you can hear it that well on a video. On the video, I think there's maybe in the last video you can actually hear the resonance peaking. But trust me, I did the experiment for you, and you can hear the resonances. I'm reading in the red here. When a system is driven at a natural frequency, we say that the system is in resonance with the driving force, and refer to the particular frequency at which this occurs as a resonance frequency. So you're going to see the resonance. What is happening? You excite the tuning fork. I'm looking right here right now. Let me put let me make it red. So I'm looking at this diagram right now. You put the tuning fork, and the very first resonance you'll get is just a quarter wavelength. So, and I've got a table of wavelengths. I might post it on there. I'm not going to give you you can listen to the video and get the data, the lengths off the video. Now, if you go to a higher frequency tuning fork, such as F2 here, you'll excite for the same tube length, you'll excite multiple nodes and antinodes, as shown here, and we're going to discover those. So we'll measure those. Now, we're not using, here it talks about the length of an air column will be varied by raising and lowering the water level in the tube. And we're not doing that. We're using a plunger and we push the plunger in to get the uh, the resonance. Here's the a picture. You can see these two young ladies. She's holding um, a tuning fork over the resonance tube, and this young lady is raising and lowering a canister of water, and the canister of water is hooked by a tube to the bottom of the resonance tube, and so it fills and lowers the tube. It's actually a very nice experiment to perform. Unfortunately, we're not able to under the current conditions. So we're gonna. Oh, they give you uh, a diagram. Not a diagram, an equation for the velocity of um, sound in air based on the temperature. Now you have one in your textbook. This is a new one. The velocity of sound is equal to 331.5 plus 0.6 times the Celsius temperature in meters per second. So if it's 20 degrees, um, as the example shows right here, if it's 20 degrees, it's 343.5 meters per second. I don't recall if I took the temperature. I think typically in that lab, it's about 24, 25 degrees, and we'll make that assumption, and we'll use that to come up with our errors, our percent error. Okay, let's see. The only other oh, you measure the inside diameter of the tube with a vernier caliper, and that's for doing the optional end effect. I am going to leave it as an optional item, but it's not difficult to do, and uh, you should try to do it. I'll give you extra points if you do the optional. Um, let's see. And the only other thing I've got highlighted here is um, the the directionality of the tuning fork. Um, if you in this case our tube was lateral, and when I had the tuning fork, in other words, you don't want the tuning fork going this way if the tube is this way. You want the tube, you want the tines of the tube to be disturbing the air molecules such that they're sort of pushing the air into the tube. And that's what they're saying here. That's a fork has directional sound propagation characteristics. And so I should have done a little experiment where I turned the tuning fork. I didn't do that, but it would have been interesting. And let's see. So um, we're gonna have uh, three tuning forks here for the temperature. You can assume, let's just say 25 degrees C. Inside diameter, I'll call the, or I'll give you that data on the fork, and I mean on the canvas, and the uh, the inside diameter. I'll give you that. The first frequency is 512, and then the next one is 1,000 hertz, and then there's an unknown frequency, and you need to figure out uh, what that is. So you're going to take a measurement here, um, and then you're going to take another measurement here, and the difference between these two is going to be 1/4 lambda. Now, every subsequent measurement is going to be 1/2 lambda. Um, so that's a two. So the difference here will be another 1/2 lambda. So the if you um, average the delta L's, you're getting 1/2 lambda. So to get the lambda, you just multiply it by two. Okay, and you do the same for the 1,000 and the same for the unknown. Then you get a velocity from fork one, a velocity for fork two, the average velocity, um, and then you use the temperature, and you come up with a percent error. And then you do the frequency of the tuning fork, assuming that the um, velocity is uh, what we measured. Um, you can come up with the uh, the frequency that of the unknown. And then you answer the questions, and that's it. This number 4 is the optional one. Again, you'll get extra points if you do the end correction. It's not difficult. It's not difficult. In other words, if you calculate, you'll come up with what a quarter wavelength should be, and the difference between what the quarter wavelength should be and what you get in this first spot, there's going to be a difference between what's expected and what you actually measured, and that's the error. That's the error that you get from the end correction, or the error that's introduced from the end correction. In other words, if you have a tube, let's make that. I'm trying to make it. Uh, oh, well, we'll just do it freehand. Uh, you have a tube. The If this is the bottom of the tube, the actual uh, resonance for the first one will be higher than the base. I wish I had used dashed lines from here to here. In other words, this is going to be your end correction. There's going to be a little bit of error there from what you measure and what you calculate that first quarter wave should be. Okay, and I think that's about it for that is optional, but I encourage you to try it. Okay, and that should be it for this introduction.